So I'll be talking about the double slit quantum mystery and its possible connection to the concept of speckles. So part of this talk was presented at the NSF-sponsored workshop at the College of Optical Sciences at the University of Arizona in Tucson. That was in 2016. Now let me discuss first the classic Young's double slit experiment. In this experiment, we have a narrow quasi-monochromatic light source, which is basically a slit source, and then there is the double slit, and on the screen you see the Young's pattern. Okay. Now the source can be an expanded laser beam. It could be a collimated beam or expanded beam, and or you can have a quasi-monochromatic slit source, but its width has to be really narrow. Okay, so that you have enough spatial coherence between the two double slits. Now, the spatial coherence length is given by lambda over theta, approximately, where theta is the angle subtended by the slit source or the width of the slit onto the plane of the double slit. Then only you can get spatial coherence. And those guys, I mean, those researchers who have claimed to have done single electron double slit experiment or single photon double slit experiment have made sure that there is enough spatial coherence across the two slits. That means they have made the slit source or the source slit narrow enough. Okay. And without realizing that lambda over theta is also the speckle size that you get in the plane of the double slit. Okay. The formula for the speckle size is also given by lambda over theta. Now, what happens in the single photon double slit experiment? If you have a single photon source, what is observed is in the beginning random dots as shown in figure A. And when you wait long enough, you find that these dots are falling on the bright bands only. Okay, very few fall on the dot. So it creates a Young's pattern. Okay, if you wait long enough. And usual explanation is the photon behaves like a wave before it enters the double slit, and then it collapses to a photon on the observation screen. Now, the problem with the above explanation is that a photon, by definition, is indivisible. It has the energy hf, according to the Einstein's formula. Now, let's assume that the photon has an extended size. Okay. And so part of the energy is going to be captured by one slit, and part of the energy will be captured by the other slit. Okay. Most of the double slit screen is opaque. Okay. The double slit, both slits are very, very narrow actually. So most of the energy should be blocked. Very little energy should go through. Okay. But then we say that finally we get a photon on the observation screen. So how can the photon have the same energy when some of the energy was blocked already? Right. Now, according to Dirac, each photon then interferes only with itself. Interference between two different photons never occurs. He has made a statement in his book on quantum mechanics. So does it mean that half of the photon squeezes through one slit and the other half squeezes through the other slit? Something physical must happen at the two slits, because we live in the real world. Quantum mechanics is great. It gives you precise results. But we have to understand that we live in the real world. So something physical has to go on at the double slit. Something physical. So Dirac has made this statement in his book that a single photon interferes only with itself. Now, I'm going to give you a totally classical approach based on the following two key concepts. The phase within a speckle is essentially the same. And I confirmed this with Professor Goodman some time back also. And two different speckles are not correlated. There is very slight correlation between neighboring speckles, very, very slight, like minus 0.2 or so. Let's forget that for the time being. Okay. So the speckle has the phase which is essentially the same within it. Now, I'm going to suggest this, that the Dirac statement should be changed to each speckle interferes only with itself. Interference between different speckles never occurs. And interference between different photons arising from the same speckle does occur. So I'm not saying the photons don't exist. Photons exist, but within the speckle. Okay, so there are multiple photons there within the speckle, and they are all correlated because they are all in the same phase. Now, the question that comes up is this: did the earlier experiments involve single speckles instead of single photons? My opinion is most likely. Now, let me give a brief primer on speckles, okay, laser speckles. So if you have a laser beam hitting a ground glass diffuser, then let's say on the observation screen, we have the angle theta, which is the angle subtended by the illuminated spot on the diffuser onto the screen. Now, the average lateral speckle size, as I mentioned earlier, it is given by lambda over theta. And the longitudinal size, that means in the direction of propagation, is given by lambda over theta square. Now, let's say we place a vertical slit in front of the diffuser, and we have the laser light shining on it. Because of diffraction, the speckles get elongated. Okay, and the theta becomes smaller in that dimension because the slit is confined to a small width. So theta becomes small, and the lambda over theta, which is the speckle size, gets elongated in the horizontal direction. Now, some are larger in elongation, some are smaller. Now, as a graduate student at IIT Delhi, I did the following experiment. My fellow students said I was crazy, but this is the one that I did. So I had a glass plate, and I put a drop of semen there and shined a laser beam from the bottom and focused it onto the semen. Why did I focus it? Because I wanted to have the illuminated spot on the semen very small, so I could get large speckles. Then the theta would be very small. The theta subtended on the screen would be very small via the mirror, of course, and I would get large speckles. And yes, I did observe large speckles, and because the sperms were moving around, the speckles were fluctuating. Okay, the idea was to place a detector there and see how many times the intensity crosses a certain threshold level, and from there be able to say, well, this person can father a child. A quick method. All right, so that was the goal. Now, if you take the case of quasi-monochromatic light source, like sodium lamp, there are speckles all over. Okay, because here we have the atoms radiating randomly, and so they are random phases, and because of the random phases, we have speckles all over. And because the phases are changing with time, the speckles are flickering. But they are flickering so fast, your eye cannot detect it. Your eye is a very slow detector. All right, so you see uniform light, but there are speckles there. Okay, and this is also what is going to happen if you have a laser beam hitting a ground glass diffuser and you rotate the ground glass diffuser, and the speckles are going to be then randomly flickering. Now, I'm going to give you an experimental proof that speckle interferes only with itself. And this is a very simple experiment anyone can do in the lab. Most of the labs have a Michelson interferometer. So here I have shown a Michelson interferometer. There are two paths, L and L prime. And I have a ground glass diffuser. And I have a laser point source illuminating it. And there is an aperture in front of it. And the aperture can control the theta. And so the speckle size on the screen. All right, now there are two speckle fields coming out because the speckle field that starts from the diffuser and goes through the aperture is going to be split into two parts by the beam splitter. One goes up to mirror M, the other is transmitted to M prime and then returns. And both of them combined on the screen. Now what we do is we tilt one of the mirrors. Okay, I have shown the speckles from the arm L as A, B, C, D, E. I've just shown few speckles, and I have shown the A prime, B prime, C prime, D prime, and E prime, which comes from the mirror M prime. And I tilt one of the mirrors to shift the speckles by one speckle size, one average speckle size. Okay, and when the diffuser is rotating, you will see that the interference vanishes actually. But if A prime and A, and B prime and B, and C prime and C, and D prime and D, and E prime and E are overlapping, that means you do not tilt the mirror, you get good interference pattern. Okay, so remember, please remember, the speckles have to overlap. That means a speckle has to overlap with its twin. Okay, that's very important, otherwise the interference doesn't occur. Also, the L and L prime, the path difference is twice that, 2 times L prime minus L, and that should be less than the coherence length, which is given by lambda square over delta lambda, or and less than the lambda over theta square, which is the longitudinal speckle size. It should be smaller than the smaller one actually. So if this longitudinal speckle size is smaller than the coherence length, the path difference must be less than that. If coherence length is less than the longitudinal speckle size, it should be less, the path difference must be less than the coherence length. Okay, so it should be smaller than the path difference, should be smaller of the two. It's very important, otherwise you can't get interference. Here is another proof. We all know, especially those guys who are working in the area of interferometry, we know that if you have an air wedge and you shine light on it, if it's a point source light, then the fringes are non-localized. That means the fringes are everywhere. Okay, there is no localization. They are sharp everywhere. But as soon as you extend the source, even a little bit, the speckles start forming. Okay, and now this figure is given in P. Hariharan's book. Okay, and I have given the references at the end. If you want to find out the plane of localization, there is a simple geometrical method. You would have the incident ray, as you can see, coming from a quasi-monochromatic light source like sodium lamp, and that ray is reflecting off the top surface and the bottom surface, which are forming the wedge, and they intersect at that point, you can see, and you just join the edge of the wedge to that point and extend it. That's the plane of localization. As you can see, I have shown speckles big here. You can see the speckle is reflected off the first surface, all right, and from the second surface, and they are overlapping right at the plane of localization. After the localization plane, you can see they separate out. Before that also they will be separated. So and as I said before, the interference will occur only if the speckle interferes with itself. So where there is overlap, you will get the interference. Otherwise, the interference vanishes. Let's go to the third proof, that speckle interferes with itself. Again, this is a thin film with the thickness T. And this is taken from Dr. Murthy's chapter in optical shock testing, edited by Daniel Malakara. And he gives this relationship T phi square is less than lambda over 4, where phi is the semi-angle subtended by the quasi-monochromatic source. It's that extended one, extended source. I can rewrite this as T is less than lambda over theta square. And what is lambda over theta square? That's the longitudinal speckle size. Okay. So and this gives good contrast. When T is less than lambda over theta square, it gives you good contrast. If it's more, then the contrast starts falling. So whenever you have an extended source and you're doing a thin film experiment and seeing the fringes, you have to have T less than lambda over theta square. I would suggest a better criteria would be 2T, twice T, because that would be the path difference. So if 2T is less than lambda over theta square, then you will get really, really good contrast. And this experiment can be done very easily also. In fact, in our undergraduate lab, we have an experiment where you have sodium lamp and you have an air wedge, and the wedge is formed with we place an audio tape at one end to form a wedge and do this experiment. And if you have a sodium lamp very near it, the contrast is really poor. You have to keep it away, or you place a slit opening there. So you reduce the phi. So this is the third proof. Now I'm going to go to the next one. This is yet another one, number 4. So here in this case, I have a diffuser, and I recently did this experiment. I have a diffuser. I have a laser point source. It's a rotating diffuser. I place a horizontal polarizer. Light gets horizontally polarized. Okay, it goes through the L1 path upward and also is transmitted to the L2 path. And I place a quarter wave plate there. So going through quarter wave plate and coming back through the quarter wave plate, it becomes half wave plate. And so the polarization rotates by 90 degrees. So now in the output light, you have a horizontal polarizer coming from the arm 1, L1, and the vertical polarization is coming from the arm L2. Okay, and if the paths are very much the same, okay, then they combine together and give you polarized light. But if you have L2 greater than L1, then you do not get it. But how much greater? If the path difference, that is 2 times L2 minus L1, is greater than the longitudinal speckle size, you cannot get polarized light because they are not correlated. Okay. And if it's less than the speckle size, longitudinal speckle size, they're correlated and you get polarized light. So vertical, horizontal combined together and you can get a polarized light. So let me point out here that if you have a quasi-monochromatic sodium lamp and you place a polarizer in front of it, let's say horizontally polarized light, horizontal polarizer, the light gets polarized, and you place a quarter wave plate at 45 degrees, you get, because you get 2 components, fast and slow, and you get circularly polarized light, right? There is no problem. Why is there no problem there? Because quarter wave plate introduces only quarter wavelength path difference between the X and Y components. And that is usually less than the longitudinal speckle size. And there is no problem there. But if you do an experiment, similar experiment that I've shown you here, you can manipulate the path difference. And you can see that if you cross the lambda over theta square path difference, then you can't get the polarization. You get unpolarized light output. The output light is unpolarized. So we have to keep this in mind that the path difference in any interferometry experiment has to be less than the smaller of the 2. Which 2? The longitudinal speckle size or the coherence length. Okay, whichever is smaller, that dominates. All right. Now we are here to explain, I'm here to explain the Young's fringes in terms of the speckle. Now, as I said before, I have the slit very narrow so that the speckle size in the elongation length, along the elongation, is greater than the distance between the 2 slits. Now, as I said earlier, the phase within the speckle is the same. So the number 1 slit and the number 2 slit have the same phase. So the phase difference is 0. And if you're on axis, on the screen, on the observation screen, you get a maxima or a bright band. The central band is bright because the path difference is 0 there, as well as the phase difference between the 2 slits is 0. So you get a bright band there. Now another speckle is falling, let's say. They are not correlated with each other, but the other speckle also gives you a bright band at the center, followed by dark and bright bands on the sides. So they overlap exactly. No matter which speckle falls, the interference pattern overlaps. And so the contrast is really good. There is no deterioration in contrast. That's the beauty. Now let's see this. Let's say, because the speckles are random, let's say speckle falls, and I'm saying at any instant of time. Okay. Now let's say one speckle falling on the number 1 slit. It will give you only diffraction. Why? Because across the width of the slit, the phase is the same, because the phase within the speckle is essentially the same. So it gives you diffraction only. The other speckle is falling on the number 2 slit, is also giving diffraction. And the two diffraction patterns are going to overlap, and you end up with a diffraction pattern only. No interference between the double slits, just diffraction alone. Now let's say I add some more speckles. So the top speckle is falling on both slits, is going to give you diffraction as well as interference. The second one from the top also gives you interference between the two slits as well as diffraction due to the single slits, the two slits. The third speckle from the top, which is at the left, as you see, bottom left, that will give you only diffraction. The bottom one at the right, on the right, which is falling on the second slit, also gives you diffraction. So some are giving you interference as well as diffraction, and the bottom two are giving only diffraction. So the ones that are giving you only diffraction, they will reduce the contrast of the Young's pattern. Okay, so it will not be a very good contrast. But if you make the slit source very narrow, most likely all the speckles are elongated enough to cover both slits, and you get a very good contrast in the interference pattern. Now, because lambda over theta is average speckle size, some of the speckles may be very small. And let's say this is the situation. These are the two slits, and the smaller speckles are falling now on each slit. Now, what is happening is that these speckles are uncorrelated with respect to each other. All right. So the diffraction also disappears. So these speckles, which are smaller than the width of the slit, width of each slit, they are going to contribute only as scattering, sort of. There will be no diffraction, because the main condition for diffraction is the phase across the width of the slit has to be the same. So no diffraction, no interference. These are going to reduce the contrast also. So you can also say that the speckles have like a dual character. So they behave like sometimes like waves and sometimes like particles, but it's not exactly particles, because wave is the speckles are basically waves. Okay, but they mimic the particle behavior if they're small compared to the object. So what did Richard Feynman miss in his thought experiment on single electron double slit? So he discusses the experiment in detail in chapter 3 of his Feynman Lectures in Physics, volume 3. Now, we have to remember that the two slits, the phase difference between the two slits must be maintained in time in order to have coherence between the two slits. Okay. Basically, that's the definitions of coherence, right? That with time, the phase difference must not change. Okay. As a special case, we can always make the two phases the same, equal. And that would result in this central band bright, and followed by, of course, dark and bright bands, right? Of course, the slow source slit can be moved, somewhere else, right? Then the phase difference will not be 0. But if it's on axis, then the phase difference will be 0. And provided the width of the slit is very small. Now, how do you make the phases the same? Now, if we consider photon or electron, whatever the case may be, let's say photon is like a spherical wave or a cylindrical wave hitting the double slit. Okay. Now, the paths from any point in the source slit to the double slit are equal within quarter of a wavelength, right? You have to have it so that the phases are almost the same there. Because if you take any point on the source slit and you join to the two slits, the double slits, the path difference between the two must be less than lambda over 4, no matter where you place the point source within the slit width, within the source slit width. Okay. Now this solution is not physically realizable. Why? Because if it is a single photon, okay, and it is how will it go through both slits? Something real has to happen at the double slits. Something physical has to happen at the double slit. So this is not physically realizable. If you block one of the slits, the photon falls randomly on the screen. So it somehow senses the slit, the second slit. How does it sense the double slit? When the double slit is there, that means both slits are open, then that photon is guided to the proper point, or the bright bands, as the quantum mechanics explains, right? But something physical has to happen. Now, the other solution is that multiple photons are coming from the source slit, okay, and they produce elongated speckle pattern that, like I have explained, and the speckle fills both slits, making the two phases the same. And since the phase within the speckle is correlated, or you can call it entangled, and some go through one slit, some go through the other slit, and they combine there on the screen. The first possibility, the first solution is not physically realizable, and Feynman missed the second solution, which is basically the elongated speckles filling both slits. If you see his derivation, he takes A and B coefficients there, and he mentions that for simplicity, let's take the A and B the same. He also states that there are some phases associated with A and B, and let's take the phases the same. Okay, but his derivation is a little bit awkward because he should have said, if the wavelength of the light source is big enough, then the phases will be the same. I'm sorry, what he says, he actually has a light source which is detecting the electrons, and he says if the light source wavelength is greater than the separation of the two slits, and then he cannot resolve which slit the electron went through, and then the interference pattern will be there. But I don't like that, actually. He should have said the wavelength of coming from the slit source must be large enough so that the speckle size becomes big, so it covers both slits, and so the phases will be the same then. That should have been the solution. Now, I'm here introducing to you a new concept, which is real-time coherence. Okay, if you read Born and Wolf's book, Principles of Optics, there is a time average that is done, and the average spatial coherence length is given by lambda over theta. Okay, but the speckles are fluctuating, actually. So if you are observing in real time, the speckle is fluctuating. The speckle size is also fluctuating. It's true that the average speckle size is given by lambda over theta, but actually each speckle is changing in size and shape. So the coherence area is changing in size and shape with time. Okay. So when you have the double slit and is illuminated by the single slit source, sometimes the speckles are covering both slits and you get interference. Sometimes the speckle is smaller, it falls only on one slit, you get only diffraction. Okay, because there is no coherence between the two slits if the speckle falls only on one slit, because the other speckle may be falling on the other slit and they are not correlated. A speckle is not correlated with another one. So it's a real-time coherence. And so how do I define the real-time coherence here? What's the coherence volume? Usually people multiply the lateral speckle, coherence length by the longitudinal coherence length. Lateral is given by lambda over theta, okay, and the coherence length is given by lambda square over delta lambda. where delta lambda is the width, spectral width of the source. That's the definition. The number one that I have shown here. This is the one. But the number two that I'm talking about is the lateral speckle length multiplied by the longitudinal speckle length. Okay. Now, the path difference must be within the smaller of the two. I have given you several proofs, like four of them, that in those ones you had to have less than the path difference less than the longitudinal speckle length. Okay. So it depends which one is smaller. Let's consider a point source. Speckle size is infinite. Then you have to worry only about the temporal coherence length. Then you don't worry about the longitudinal speckle length because that's infinite. And the coherence length lambda square over delta lambda is much smaller. And so you are limited by that. And that's what we do, when we have a point source of light and you have a Michelson's interferometer, we worry only about the temporal coherence length. But if you have a diffuse source, you have to worry about the speckle also, longitudinal speckle length also. If it's smaller than the temporal coherence length, then the temporal coherence length goes out the window. Then you have to worry about the longitudinal speckle length. Also, a corollary, a very important corollary comes from there. When you have unpolarized light, you can get interference from unpolarized light. You can split the beam into two parts by a Michelson interferometer and combine them and get interference. Right? But if the light is unpolarized, that means X and Y components of the field are uncorrelated. Right? But if they are uncorrelated, how can they interfere? So the corollary that I'm getting here is, or I'm coming up with, is the unpolarized light. It is polarized within the smaller of the speckle volume or the coherence volume, whichever is smaller. I remember I asked this question to Professor Wolf many years ago. So it was like 20, 30 years ago in a conference. Is the light polarized within the coherence time? And I was referring to unpolarized light. So unpolarized light, is it polarized within the coherence time? I was not able to get the proper answer. It is polarized within the speckle volume or the coherence volume, or the speckle length, longitudinal speckle length, or the longitudinal coherence length, whichever is smaller. So when you have a point source of light, you don't really care about longitudinal speckle length because the speckle is infinite in size. Then you worry only about the temporal coherence length, which is the standard lambda square over delta lambda. With a diffuse source, you have to worry about the speckle length also. So it's a very important corollary. Now let's go to the which path information. People say that knowing even in principle that the speckle, in the case of electron, if you replace the speckle with electron or a photon, they will say, okay, even if you, in principle, you know that a photon went through one slit or the other slit. That means if you can pinpoint whether it went through number one slit or number two slit, it is sufficient to destroy the interference for the speckle, for that electron or photon, whatever it is. But if I replace the single photon with single speckle, then we can say the same thing, knowing even in principle that the speckle hit one slit, it is sufficient to destroy the interference for that speckle, for that particular speckle. It is not necessary to find which particular slit the speckle hit. Okay. Now, how do you know in principle that the speckle is going to hit only one slit? It's very simple. If your source slit is small, the speckle length will be big. It's most likely going to hit both slits. If you increase the width of the slit, source slit, then the speckle size becomes small. The elongation becomes smaller. It may not hit both slits because it may be smaller than the separation between the double slit. So it works out good. The same statement. Now, let's see this. here, the second statement here. Knowing even in principle, now I'm replacing again the photon with the speckle, but let's go back to photon first. If you have a single photon experiment, which people claim to have done, and they place a polarizer, vertical polarizer on one slit and a horizontal polarizer on the other slit, the interference disappears. It is true. And if they place a 45-degree polarizer in the output, the interference reappears. And the explanation that is given is that we have labeled the photons now. And because we have labeled it, we know by seeing the polarization, checking the polarization of the photon that comes out. If it's vertical, we know it came out from the first slit. If it is horizontal, we know it came out from the second slit. And that is sufficient to destroy the interference. That's the reason people give. Now, let me say that cross polarizations do interfere. We always teach in our undergraduate or graduate optics that cross polarizations do not interfere. They interfere, but we don't see the interference pattern. Why don't we see the interference pattern? Because there are polarization bands there. There are polarization changes there on the screen. That's why your eye is not sensitive to polarization changes. So the polarization bands, as I've shown you, plus 45, minus 45, plus 45, minus 45, these are the interference bands. I call it polarization bands because you cannot see them. When you place a polarizer, which we call an analyzer at the output, at minus 45 or plus 45, these alternate bands are going to go through. Light will go through. And it is converted to bright and dark bands. It's a simple explanation. Those people who work in the area of interferometry may already be knowing this. So when we say cross polarizations do not interfere, it's not true. If you have an eye as a detector, then okay, you can't see it, right? Because eye is not sensitive to polarization. But the polarization bands are there. In fact, the plus 45 and minus 45 bands are not sudden transitions. They go through the elliptical and then go to circular and then go to from plus to minus 45. It's a gradual transition. All right. Similarly, there's another paper that appeared in 2002 where they placed a right circularly polarized light on one slit and left circular polarizer on the other slit. And again, the interference disappears. And again, when you place it in the place a polarizer in the output, you get back the interference pattern. In this case, of course, you can place the analyzer at any angle. And as you rotate the angle, you can see the interference pattern shifting actually. In this case, you don't have to put it at 45. At any angle is fine actually. Okay. But the explanation that is given that we know that the photon went through this slit, that's why the interference disappears, I don't like it, tell you the truth. So how did Elaine Aspect experimentally distinguish between particle and wave behavior? He just placed detectors there and the light is incident. The photons are coming in, going through the beam splitter and reflected. Okay, and if the photon, and it's connected to the detectors are connected to a coincidence circuit, and if there's anti-coincidence, that tells you that it's a particle behavior, right? The Wheeler's delayed choice experiment is shown here. Okay, if you remove the second beam splitter, this is a Mach-Zehnder interferometer. If you remove the second beam splitter, then I'm assuming a speckle is coming in, and speckle will split into two parts. One will go in one arm, the other will go in the other arm. They are twin speckles, basically. You can call them twin brothers. Okay, they are correlated because they are coming from the same mother speckle. If you have a beam splitter, you will get interference because they will combine together. And we know a speckle interferes with itself. And they are the twins actually coming from the same. So they are correlated. They will interfere. If you remove the beam splitter, of course, one speckle will be detected from the top detector, and the one will be detected on the right-hand side shown there, right? And if you have misplaced the detectors a little bit, you may get anti-coincidence. So you have to be really aligned to get coincidence, actually. So that could have happened. A slight misalignment of the detector will show you anti-coincidence, and you say, oh, it's a particle behavior now. And when we put back the beam splitter, we say, oh, now the photons know that they have to behave like a wave because the beam splitter is there. And so we are going to interfere, right? And the arms can be very long, actually, and the beam splitter can be introduced electronically when the photon has just crossed the beam splitter. So how does it make a decision? Then suddenly the beam splitter appears. Oh, I have to behave like a wave now? That's very strange, actually. Now I'm going to talk about Vancitozoniki theorem. This is a very interesting theorem. And if you have a slit source, then you get a curve like this for the coherence. And if you separate the 2 points, P1 and P2, by an appropriate distance, P1 is falling at the center and the P2 is falling at the dip, which is negative, actually. It shows like a negative correlation of -0.2. And you get the reverse contrast. That means bright band appears to be, changes to dark, and dark changes to bright. And of course, the correlation is small, so the contrast is also small. And this has been observed, right? So if the 2 pinholes, P1 and P2, are placed closer than this distance as shown, then of course you get good contrast. Now, if the contrast keeps going down, if you place it where the curve intersects right at the axis, on the axis here, of course the contrast will be 0. And then when you come here, the contrast reverses. This is because the nearest neighbor speckles are anti-correlated, somewhat anti-correlated. Okay, so even though I mentioned to you earlier that the speckle interferes only with itself, but there is a slight correlation between just the nearest neighbors, very slight. I had neglected that when I was discussing, because that correlation is extremely small. But that explains this by Vancitozoniki theorem, contrast reversal, very beautifully. Now, all of the above applies to matter waves as well. Example, a vertical tungsten filament will produce horizontally elongated speckles of electrons. Some electrons are going to go through one slit, some will go through the other. And remember, please remember, the speckle, all the electrons within the speckle have to be correlated because the phase has to be the same. The above conclusion applies to sound waves too, as long as one is able to produce a quasi-monochromatic, spatially incoherent sound source. So if you can produce, it may not be easy, but if you can produce somehow a spatially incoherent sound wave, like a quasi-monochromatic sodium lamp source, you could get the same effect from the sound waves also. That means the speckle has to go through both slits in order to get the interference of sound. So conclusions for a single speckle two-beam interference experiment. Most likely single speckle two-beam interference experiments have been done instead of single photon. Dirac statement should be changed to each speckle interferes only with itself. Interference between different speckles to a large extent never occurs. Interference between different photons arising from the same speckle does occur. I would suggest that please go to the Nobel Prize lecture by Roy Glauber. Okay, I think it was 2005. And I can show you the clip here if I have the time, but let me just at least point out here that he makes a statement about Dirac's statement that each photon interferes only with itself. He says it's nonsense. So please go and view that lecture of Roy Glauber. Now, the polarization labeling a speckle which falls on both slits will still produce interference in the form of polarization changes or polarization bands, which can be converted to intensity changes by an analyzer in the output plane, as I discussed earlier. The concept of speckle interference essentially gives the physics behind the spatial coherence, the mathematical counterpart of which is the Vancitozoniki theorem. All of the above conclusions are valid for matter waves. And the above conclusions are valid for sound waves also, as I mentioned earlier. And the beautiful corollary that comes out is the unpolarized light is polarized within the smaller of the speckle volume or the coherence volume. I have these references here in case you want to go through these references. In the number 12, if you see, this is a book edited by Dr. Roy Chaudhary. And there's a paper there, number 10, Panarella. And he mentions that the single photons have not been detected. And he tries to explain the double slit mystery with the cluster of photons. Okay, but it's not the same as the speckles. All right. So I suggest you see that. I'll show you a small clip actually where he mentions that. Here.
The dilemma is very neatly stated in the first pages of Dirac's famous text. He's talking about the Michelson interferometer and says that each photon then interferes only with itself, and interference between two different photons never occurs. Well, forgive me, this is quantum mechanical scripture, but it is also nonsense. The things that interfere are not the objects themselves, they are the amplitudes for certain possible histories. And indeed, such amplitudes can be constructed for pairs of photons, triples of photons, what have you.
So thank you so much. That's the end. Thank you so much.